I'm Brett Sackett, and this is Ann Hanks.
Yes, we're physics at PASCO. So today we're going to be talking about the Blackbody apparatus. I have to tell you that I got the idea for this at the Exploratorium in San Francisco, and I saw them do this, and it was like using an Apple II computer, and I don't know what sensors they were using. And I thought, well, if they can do it, I can do it. Well, it turns out it's really hard to do. So I guess that's why people actually purchase this from us. I'm going to start out by explaining exactly what this is that you're seeing in front of you. The first thing that's here is the Blackbody light source, and I have it locked down so that it wouldn't flip off here. It's just a light bulb.
With a tungsten filament?
Yes.
So it's a broad spectrum that it's emitting.
But it's definitely not a black body. Not for real. I wish we could sell those. Anyway, this is being powered by the 850. In this case, the 850 turns out to be a really useful piece of apparatus because we're powering the light source. And so I'm applying right now 7 volts. It's like a 0 to 10 volt light. And I've got a voltage sensor across the bulb so that we can measure the voltage. And because this is being powered by the 850, it's also measuring the current through the bulb. And with those two things, you can get the resistance of the bulb when it's running. And you can calculate then what the temperature of the filament is from the resistivity. Mm-hmm. And you can arrive at what the blackbody temperature should be. A little bit more about that later. Anyway, the other thing we're using this for, and by the way, this voltage sensor is our new UI voltage sensor, which is auto ID. When you plug it in, it knows that it's a voltage sensor. Then we're also using passport sensors. We're using a broad spectrum light sensor. And so broad spectrum means 350 nanometers to 10,000 nanometers. Mm-hmm. And it's a thermopile, which means that it does heat up during the experiment. And that's why you don't want to spend a long time making your scans because then it will drift on you. So we're using that passport sensor plugged into the 850. And then we're using a rotating motion sensor, which is also passport blue. And that's because it has 4,000
divisions per revolution.
Divisions per revolution, thank you. And then we're measuring the angle that we're turning to with this. There's a pinion here which turns 60 times every time we rotate the platform once. So it gives us a mechanical advantage and makes it so that we can see with the angles more precisely. So the first thing that the light goes through is a collimating slit, and then the light goes through a collimating lens so that the rays are coming parallel out here. And then they hit the prism, which I see is been knocked out of alignment.
All right, who did it?
Yeah, well, I'm going to blame you, but I think it was me. Anyway, the prism is held on to the
the plate.
The plate with a screw. And,
Oh, we'll get the other plate.
yeah. And I'm just seeing, I think, and then there's a,
so this plate allows us to attach components on top of the plate, and you can secure it underneath with a wing nut. And what that allows you to do is to keep the component fixed in space while you rotate the plate below it.
yeah.
And so that's what's happening here is the prism will stay in one fixed position, but we can rotate the armature and the plate and make measurements around it as the collimated light goes through the prism.
So when you're setting this up, you want to make sure you don't screw this all the way down, because then it will lock it in place and won't be able to move.
Right. That's why you have the wing nut underneath to kind of lock it into place.
And the prism should be have its apex pointed at the light source.
And then on the side of this plate is a spring-loaded door that the Passport rotary motion sensor mounts onto, and that spring-loaded door keeps the pinion against the plate. So it always is in contact with the plate, so when you're rotating it, it's rotating the pinion.
So then after the light is spread out by the prism into all its glorious colors, there's a focusing lens that focuses it onto this aperture bracket, we call it, on the light sensor. And the aperture bracket has another slit that is there so that you can narrow down how much of an angle you're looking at, so that ideally you'd want to look at one angle at a time and not several, that would be several wavelengths. But sometimes you have to open that up a little bit in order to get enough brightness, depending on how dim the source is. Now, let me rotate this over here.
There it is.
Oh, there it is. In fact, can you turn out the lights for a second? So here is, can you see that? Are you able to see that?
I seem to find it.
Zoom all the way in, it's right in the center. Perfect.
So that's the spectrum being bent off, refracted from that prism. The Blackbody setup comes with the factory calibrations of what the prism's index of refraction is for different wavelengths. And then there's an equation that you use to translate the angle that you're reading here into a wavelength. So,
And you'll find that in the capstone file in the calculator.
right.
Also referenced in the manual.
Yeah. So I have a capstone workbook set up for this. This does use capstone, not what's the other program called?
SparkView?
SparkView. Because SparkView doesn't handle an 850, so you have to use this. So the workbook has the theory of what the spectrum should look like as a function of its wavelength. And it's dependent on the temperature, T. And then there's the setup in here, so you can set everything up. And then there's the procedure that tells you how to get the data. But let me just take you through the basic procedure. The rotary motion sensor reads 0 degrees when you start it. And one thing we should have mentioned is that on the bottom side of this arm, there is a, what's the other program called? SparkView. stop that we installed for this experiment, so that when you go all the way over to the degree marker, it stops the arm from moving. This gives us a beginning point for our scan that can be the same for all
Yes.
scans.
Because you want to do it for different temperatures.
Yes, you want to do it for different temperatures. So the next thing you do is turn it up to 10 volts, then you turn it down to 4 volts, and you scan it 3 times at least. So you always start in this position, hard against that. And just to show you what, well, you know, I'm probably not going to be able to get real good data, but we'll do this. You pull this hinge back, and then you force the rotary motion sensor towards the hinge and tilt it as far as it can go, and then tighten these screws. If you tighten them well, then when it springs back against here, there will be enough pressure to keep it in contact the whole way. So obviously it was losing contact somewhere along the line there. It looks like it's turning now.
Okay.
All right, so rather than go through that one more time, I'm just going to show you the data that was collected before. This green run that you're seeing, let me take the other one off. The green run is the pure light intensity versus angle. And in order to make that into the true angle, you do a calibration run. So instead of that, we do this. And the calibration run is done by simply tearing this, and then, well, you're supposed to start on, say, like 50 degrees. There's a little indicator here that I can read. And so you start on 50, you tear it, and that's just so the light sensor is in the right range. And then you can do this in the light, of course. Then you rotate it completely around to 50 degrees on the other side, so that you've gone through, I've got some sticking here, to 50 on this side. Then you stop and you let it sit there for 10 seconds, because the light sensor is going to sit there and drift a little bit, and it will make a nice little vertical mark where you ended. Then you can go, and that's what is being shown in the graph here. It shows you very distinctly where it ended, so that you can take a coordinate tool and put it on that. And it will tell you exactly how far you moved it. This happens to be in radians, and I just did 100 there. This is in degrees. So it says that I went 5,985.45 degrees. Obviously I didn't. I only went 100 degrees. And so you use that ratio in order to calculate your actual true angle that you're going through. So in this second graph here,
So you're using that calculation instead of the pinion calculation. You're just
Right.
using your own calibration curve.
yeah. And so this is plotted versus the true angle, as it says. Then the other thing you need to know is, what is the initial angle? Where is that center on this, so that you know how much you're moving out to the light. And so you just use the cursor to find that angle in the true angle, and you put that in the calculator. The calculator is open over here, and there's a place to put the initial angle, And I'm not going to change it from what it is because I already typed it in one time before. And then in the analysis page, here's showing 3 different runs. And it's plotting relative intensity from this light sensor and versus wavelength. But the wavelength is calculated. So it's calculated from the angle, and the calculation for that is in here. It's pretty small, so I'm having trouble seeing. Oh, there it is, wavelength. Line 7 has the wavelength calculation on it, and it uses the information from the manufacturer of the glass to know what the index of refraction is for different colors. Now, there's an interesting thing here in this calculation. It says lambda equals, and the nice thing about Capstone is you can put Greek letters in. I'm so happy. Now, whenever I'm using Word and stuff, I try to right-click to put it in a Greek letter, and they don't have it. Anyway, it says lambda equals filter 400 to 2500. And what that's doing is only showing you on the graph here anything that's between 400 and 2500. We took more data than that. We took data over a long range because we had to find that center spot. But this is just a calculator way of showing you just the part of the data that you're interested in seeing. So this is, the top one is the 10 volt run, the middle one, the green one, is the 7 volt run, and then the coldest one is the 4 volt run down here in blue. We actually chose those colors, red, green, and blue, because red's hot, blue is, so we chose to put them in that color. Now, what the Blackbody curve should look like is actually slightly different than this for many reasons. One of the reasons that we're putting the filter on and only going out to 2500 nanometers is because the glass doesn't transmit that past that anyway, so you're not going to get any more of the infrared. Plus, you don't want to pick up the infrared of the room, so you got to be careful. So we are probably not getting exactly all the light that would be coming through from a black body, but this isn't a black body.
It's a close approximation.
So, that's why the curve is not going to be exactly right. Now, there's a lot of questions here about what happens to the peak when it shifts. It shifts when you cool. But further in the analysis here we go. Here's a case where the 10 volt run is in the dark red, and then a theoretical curve in green. So
for a true black body.
For a true black body, with the temperature that you've calculated that temperature is, the green should be the actual curve. And you can see that we're not picking up all the UV, or the bluish part of the spectrum, and it's knocking out some of the infrared too. So it's not perfect. But you can at least see how it varies from an actual
and as you
body.
Change the temperature, you can still see the peak shifting.
Yes, you can. Now, I mentioned about the temperature. This is a sticky point that people have trouble with. we're measuring the voltage and the current through the bulb. But of course, that voltage is right across the bulb here, but it includes the holder.
Mm-hmm. Yeah.
And you can't really include the holder in this experiment. So you need to determine what the cold resistance is of the holder by actually taking it apart and, just having the holder part in there.
Okay.
And then you also need to know the cold temperature of the tungsten. So that's another measurement that you take while it's not turned on.
Mm-hmm.
And then you get the adjustment from when it is turned on. You do V over I to figure out what the resistance is of the bulb when it's on. And from that, you can determine what the temperature of the bulb is. So if you're careful and take out all the other factors and don't measure your voltage back here, measure it close up to the filament, you can get a reasonable answer for what the filament temperature should be.
Grounding. I don't think we mentioned the grounding.
Oh, we didn't mention
Yeah,
grounding.
let's. Oh, there we go. We got to mention the grounding.
Helps if you
Yeah.
actually do it. There's a grounding stud here so that you can attach it to ground. I'm using the ground on the output here. It's connected to the ground in the wall of the 850. This grounds the entire apparatus. It's all metal, and in fact, even the sensor has the nut that you're screwing into has a wire into the circuit to make sure that when this is screwed down on here and this is attached to ground, that part of your circuit is
Right.
attached to ground.
Keeps everything quiet.
Yeah, it keeps it quiet because this does act like a little electrical antenna, and it will give you all kinds of results that are fluctuating if you're moving near it. And, but that eliminates that problem. So,
All right.
questions? Do we have any questions? Probably going to ask us what this is for, but that was from the last one.
Is the spectral response curve for the 2150 sensor known? For the light?
Yes, it is. And so you could compensate that way too, right? We're already doing that as much as possible by making it a sensor. We're trying to take into account that spectral response.
Can you use a temp sensor to measure room temperature to use at your holder temp and filament temp?
Can you use a temp sensor to
use
get
that
the
as your
ambient
holder temperature.
temperature and get the holder
Yeah.
temperature?
Well, most people know what room temperature is. And considering that this is up at 5,700 degrees, not too worried about being off a little bit on what the cold temperature is. So I would just use room temperature. And of course, you got to do that while this is still turned off.
Right.
I think that's it.
Okay. Guess that's all the questions we have. So we're going to take another short break, and we'll be back
With
with
the
the
interferometer.
interferometer. Thank you.